Yeah. So this week, there was a pandemic, and we were all using Zoom. And it occurred to me that we all changed how we taught using Zoom. And then we're now back to teaching in person. So there's probably things we learned last year that we can bring over into the in-person era. So I asked around for people that had ideas or things people had tried to develop earlier, but they actually really developed in last year and so on. And one of the ideas that came up was that math are thinking of how to reorganize their big courses. So it's not completely connected to Zoom, but it all snowballed in the last year. So I asked Fok-Shuen to come along and talk to us. So he's going to talk about how to teach large classes with limited resources. So.
Thank you. So I think the microphone is on, but can you just give me a thumbs up in the back of the room if you can hear me? Okay. I normally pace quite a bit as well, but I'm told that for the camera view, I'm supposed to stay behind the desk. So I'm going to stay roughly. I'm going to stay roughly.
We'll see your slides and it doesn't matter.
Oh, okay. So my apologies to the Zoom people. At some point, I may start pacing, but I'm going to try and stay behind the desk. So I'm a faculty member in the math department and the undergraduate chair there. And as Doug has mentioned, I'd like to talk today a little bit about teaching too many students with not enough resources. Now, when I came up with the title a few days ago, I thought that this would be kind of catchy and spicy and controversial. But on review, it's kind of the least controversial thing, right? I mean, everyone is teaching too many students with not enough resources. So this is not a particularly new problem, but I think we're doing some interesting things in math, and I thought it'd be a good opportunity to take this time to describe what it is that we're trying, and maybe to get a little bit of feedback from you. I've divided this into slightly kind of frivolous sounding chapters because I've been watching a lot of Wes Anderson movies. So that's why these things are called the way they are. But roughly speaking, I want to describe the landscape of teaching in the mathematics department. I want to talk a little bit about a thing that happened 7 years ago in a much smaller setting. I want to talk about its descendant, what it's going to look like going forward, and then maybe at the end, draw together a few broader points. Throughout, I think the audience is small enough that if you have questions, maybe just jump in and ask them. And Riley, right? Riley? Maybe if there are questions in the chat, just go for it as well. So I'm going to pin this from about 10 years ago. So since 2011, we saw more students taking calculus. So in 2011, winter term 1, we had just over 3,000. This current term, steady state, so with all the drops and things like that, we have about 40%. Which in and of itself is not so alarming, except the number of instructors has not grown by 40%. We have a handful more faculty members, but we actually have fewer postdoctoral fellows and fewer graduate students. So our bench is shallow. But the number of sections has remained roughly the same. Or not but, therefore the number of sections has remained roughly the same. And we have this principle in the math department, maybe a little bit more firmly established in the last few years, that novice instructors should have these hard section caps. Now I should pause here for a moment and say, for our colleagues in physics, that in math we often give full sections of a course to graduate students, and we very often give full sections of a course to postdoctoral fellows. So they're told, you're going to teach section 207 of Math 101, integral calculus. You're going to do it Monday, Wednesday, and Friday. You're going to get some support, but go. So this is not a TA position. This is a full instructor of record position. Now we have section caps, 80 for graduate students, 120 for postdocs, at least in first year courses. These caps shrink very slightly for second year courses, and then third year courses, they're small. But because we have these caps, that means that the faculty sections have roughly doubled in size. So 10 years ago, a differential calculus class faculty section would have been just over 100. And now on average, it's just over 200. And we have calculus sections that range all the way up to 480. Very, very big sections. That's one of the issues. I would say that the bigger issue is the one for novice instructors. So the cap notwithstanding, the section is just too much. So what happens in the room, even with only 80 people, is not really the issue. I think those of you who teach will know this, right? The bulk of teaching at the first and second year level is the stuff that happens around teaching. It's the maintenance of the grade sheets. It's responding to student inquiries, most of which do not have to do with the material, not have to do with kind of the curriculum, but they don't have to do with math. It's keeping up with the other sections. It's making assessments, and so on and so forth. Now, this is something that novice instructors just find overwhelming because, frankly, it is overwhelming. And so they don't really have time to focus on their teaching. For faculty instructors, it's a little bit better, but the sections there are just too big. 240, 360, 400 students. The scale is just overwhelming, especially for the one faculty member who's in charge of all 10 sections of differential calculus for physical sciences and applied sciences students. But this is, it really is, it's a task that can break you. It's one where if someone does it for a few years, we kind of have to promise them that we'll never do this to you again for a little while.
So how big is that cohort, you know, all the sections together? Is it 1,500? Is it?
Yeah, good question. So how big is the cohort?
Repeat the question,
Yeah.
because the people in Zoom want.
So the question is how big are these cohorts? For our largest cohort, which is Math 100, it's 1,700 students. Our smallest of our main cohorts, which is Math 102, biological sciences, has been 800 students. Okay, so we've got this thing, right? We have too many students, we don't have enough resources, it's hard on everyone. So having laid out this fairly desolate landscape, what I'd like to do is I want to take a step back and I want to talk about the sandbox. So the sandbox I have in mind here is this little kind of jewel of an experimental space that didn't quite turn out to be what was promised, but I think some good came out of it. And here I'm talking about Vantage College. So in 2014, Vantage Math, where we were given kind of lots of resources and very little oversight, it was taught using what we're going to call the small class model. So differential calculus, integral calculus, to a smallish class of around 100 students. We did this for a number of reasons. We really wanted to kind of communicate, give students a chance to communicate with each other. And we thought that this 100 students was going to grow to 400 and then 1,000 students, right? So we were kind of planning for a lot of growth. It stuck around 100 students, but it did give us this chance to iron out the kinks. So this model, this small class model, it blends large lectures and small classes. In its first iteration, it was quite a bit more luxurious than what it looks like now. And the motivation is we thought like the teaching that in many cases excites us the most is the teaching that we give the most resources to. I mean, in some sense, you give the most resources to it because there are only a handful of people who are going to learn topology, right? But nevertheless, there's something kind of magical about a grad seminar that's kind of crackling. Students are doing math as well as watching math. They're generally working together. When these seminars work, there are kind of ideas. There's math taking place in the room. And it's not that you're just kind of carving out space for math to take place when students go back to their residence. So in the model we basically separate the contact hours in a week. The lectures are a little bit larger, all students attend them. And we have this thing called the 80-20 rule. So in a lecture, at best, it's about 20% active, where students are talking to other students, where the flow of information isn't kind of along this axis, but all mixed up in the classroom. And the idea of the lecture is supposed to lay out theoretical groundwork. It's supposed to do the theoretical heavy lifting. So in a differential calculus course, it might be something like in the lecture, you're introduced to the chain rule. And then in the small classes, you might take the idea of the chain rule and for the first time, so this is not a workshop, it's not a recitation where you're doing stuff that you've done already. You're learning new stuff. So in the small classes, for the first time, you might encounter the notion and define implicit differentiation and then look at inverse trig functions for the first time. And the small classes are taught by 2 people in the room, 1 novice instructor and 1 undergrad TA. The 80-20 ratio is reversed. So at most, you can spend 20% of the time talking to students. And even then, we really strongly recommend that you don't talk to students the way I'm talking to students, that you talk to students from somewhere else in the classroom. The whole point of the small class is it's supposed to sort of disrupt a classroom space. The instructor's supposed to be wandering around. People are supposed to be writing on various surfaces. It's not supposed to be this thing where there are a bunch of people here like an audience and then a performer. In the first iteration, there were 4 contact hours for Vantage students. There was 1 lecture hour, 2 small class hours, and then this extra workshop hour that was like a genuine recitation, where they were doing stuff they'd seen before. In the second iteration, we got rid of that 4th hour, because we found that those small class hours were just so rich and so valuable that we didn't need the 4th hour. I say rich and valuable, I should say that in the small class hours, it always feels like you're going slowly, because you are going slowly. But everything that happens there is just way stickier than in the lecture, right? There's this really tempting thing, at least for me, and I'm sure instructors are kind of sympathetic to the way I teach, where you can sort of fool yourself into thinking that a lot is happening because you're talking about a lot of stuff, and then you assess students on it, and it turns out they learn none of it. In the small classes, this rarely happens. It turns out it feels like you teach less stuff, but all the stuff obtains, which is great. So this is the little experimental space where we tried out this model. And then we asked, okay, so we've got this kind of nice idea. The Vantage students seem to like it. The instructors really like it, particularly the novice instructors. And when they're shipped off to kind of mainstream upper year math courses, they do well. So let's be a little bit more rigorous about it. We want to ask a couple of questions. Will it work for mainstream students? And will it work for bigger courses? So at our first swing, we tried it out on direct entry students. So mainstream math 101 was taught the same year. I'm sorry, in 2017. So this was a section of 107. And I'm going to pick out the 98 in science. We had 4 small classes. All assessments were otherwise the same. In particular, the final exam was the same. Now I'm going to pick out the students in science because we compared it to the other students in science. So we've got 613 students in the 1,300 Math 100 students in 2017. We ignored the applied science students because they defy all the characterization when it comes to sort of experimenting on them. Right? The applied science cohort effect, as you know, I think, is so strong that it's kind of impossible to control for. In addition to that, in the experimental section, we just had so few applied science students. And with that, yeah, let's just ignore it. There were 9 instructors. The bench was pretty diverse. There's 1 grad student, 4 postdocs, 4 tenured faculty members. And the tenured faculty members, like it's not like we had the experimental section and a bunch of potatoes. And these were good instructors, very, very solid instructors. And what we did is we looked at performance on the final exam, adjusted using linear regression model based on their Calculus 1 grades. As it turns out, the incoming grades from Calculus 1 are very, very similar. So we washed the data through the regression model and not through the regression model and found more or less the same thing. So the experimental section had an incoming Calc 1 grade average of 67.3, 67.2 for the rest of the sections on average. And very, very similar standard deviations as well. Okay. So we've got this experimental section running, we've got 9 standard sections running, and we want to look at how they do on the final exam when we control for incoming skills as measured by their performance in Calculus 1.
So, did the students know that this section was special when they signed up?
They did not.
Okay.
Yeah.
Okay.
Oh, I'm sorry, did they know that it was special when they signed up? They did not know it was special. Yeah, so, I mean, not only do we not tell them, but in math we have this, I'm gonna call it a tradition because it's a thing that's happened for a long time and I'm not sure why it happens, of releasing instructor names very, very late. Yeah, I don't know why we do that. We do that. Oh. So, without and with the adjustment using the regression model, the experimental section just did better. Now, they did quite a bit better, and so the probability, what is it? The probability that this is kind of coincidental is very, very small. The p-value is very, very small. I will point out, and this should probably be a topic of another talk in the math department, that when I say they did much better, I mean that they got like a mighty 48.6% on the final exam versus a 43%. Now, you know, it's tempting just to gloss over that point, but I will say that as our siblings in the Faculty of Science, I think we really perform, in the math department, I think we perform a crucial role in maintaining a particular standard. And we get no thanks for it. So, I mean, I feel like we should get more love from our sibling departments for doing this. Because the standards of our exams are just, they're ratcheted, I would say, ever so slightly downward over the years. But they're still there, and this is why we get, I mean, this explains many things, right? It explains these averages, it explains a great deal of Reddit, probably, things like that. But anyway, the experimental session did better, but by better, I mean, they're just shy of a passing grade. And then we asked a couple questions. Were they lucky? I'm sorry.
You ended up scaling or something.
Yes. This is the final exam. Yeah, and that's right.
No, but not their final mark.
Not their final mark. No. Even in math, we would not do that. So we asked a couple things. Was this gain just due to luck? Right? And it wasn't. So we did the same data analysis using other sections as the experimental section, comparing it to the rest of them modulo the experimental section, and found no significant difference. Was it, and this is more or less the same question if you dig into it statistically, but was it coincidental? In other words, was there just one section that in some really funny way tanked the average for the standard sections? And again, the answer is no. We did these head-to-head comparisons. By the way, on the second point, I should also say that we did this for the previous year. We did it for 2016, and found that in 2016 there was just no appreciable difference between any of the sections. So there is something particular about the experimental section. Yes?
Yeah, I was just going to say, so I think we've noticed a difference in sections based on the registration time.
Yeah.
The 8 a.m. classes fill up later, and of course, students get to register earlier if their high school marks are higher. So there tend to be more weak students in the less desirable time slots, like 8 a.m.
So you try to repeat, sorry.
So I gotta keep remembering to do that. Sorry. So the question is, was there any? I don't know. Could this have been affected by the effect of weaker students getting later registration times?
Ending up in less desirable sections.
Exactly. Yeah. And so 8 a.m. being filled with weaker students. It appears not to be. In fact, that effect, at least in Math 100 and Math 101, which is where we've looked at it, appears to be overstated. At least when it comes to final exam performance. Maybe throughout the term, I don't know, they work harder or something, but even though there are definitely weaker students in certain sections incoming, by the end, this appears not to be the case. In any case, the final grades were adjusted by incoming Calculus 1 grade, right? But the adjustment did almost nothing, so. Yeah, good question. Yeah, so.
What about teaching to the test being a thing? Because, I mean, sometimes that's, you teach something differently and it turns out one person is just basically running through last year's final over and over again.
Right.
And then they do better.
So the question is, what about teaching to the test? I guess that's always a possibility, but the tests for these, or at least in this year, the test was designed by the instructor in charge fairly late. So there simply was no test to teach to for most of the time. Okay, a couple of just interesting points about the experiment. The benefit was biggest for the strongest and weakest students. It was the most significant for the strongest and weakest students. We have a couple of conjectures why that's the case. A little bit less rigorous is this observation about the math attitudes and perception survey. So this is a math version of something that I understand was developed as a physics tool. It generates a grade between 0 and 1 for a student who answers a battery of questions. And 1 indicates perfect alignment with the attitudes and perceptions of professional mathematicians. And 0 indicates perfect non-alignment. Sorry, I should ask the audience, there is a physics version of this, right? Because I'm pretty sure Warren Code and others more or less adopted your version. So PAPS or FAPS instead of MAPS. Actually, it's not called that. But anyway, okay. So we have maps. And this
It's called class or something.
Jim says it's called class.
class, okay. Oh yes, yes, class with 1 S, right?
2 S.
Okay, you're right.
Michael Dorado University.
Yeah, okay.
Online was more.
Okay. Anyway, this is the math version of that. In the experimental section in this case, it registered the only positive shift in maps. At the time, I think this has since been overturned, but at the time, it was in fact the only positive shift ever recorded. But anyway, it's a fairly significant shift. Remember that this is a score out of 1. I think even more interesting, but slightly less significant, like statistically, is how the shift was registered. So we've got these 7 axes for maps. Confidence, mindset, real world. So how much you think math relates to what you see every day. Interest, persistence. Sense making, which is different from real world. So sense making is like some measure of how magical you think the subject is. By magical, I mean like, I do some things, I don't know what's going on, but it generates an answer, and that answer is math. And then answers, how important you think answers are. So the blended section, it had these unique losses in confidence and unique gains in persistence, and that is against the run of play. So normally maps goes down, but in all other sections, students gain in confidence and lose in persistence. Now this, to me, is actually a very hopeful sign. I mean, if I thought a priori of what I wanted my students to encounter in a math class, I really would want them to get more persistent and less confident, because they don't really know stuff and they have to learn how to know stuff, and this is the way to do it. So 2 conjectures. The first is that small classes make students communicate, and this is good for top students. So I think, as you all know, particularly those of you who teach 1st and 2nd year courses, I mean, a very great way of subverting the enthusiasms of your top students is to say, like, go and answer some questions on Piazza. It's very, very good for other students. And it turns out it's quite excellent for the top students as well, right? To be able to articulate what it is that they've learned. They've seen one, they've done one, and now they're teaching one. Sorry, that's not correct, right?
No.
Okay. I'm just getting my phone out here. My apologies. Okay. The second conjecture is that small classes for weak students, it gives them an hour or two every week where they have to sit down and do stuff. And someone is holding them accountable. But someone is supporting them as well. So they can't, or at least it's harder for them to convince themselves that everything's going to be okay when it comes to the midterm because they'll cram for the midterm or something like that. And maybe they even get in the habit or get out of the habit of thinking that way, right? Maybe they get into the habit of thinking, you know, I can do a little bit of this every week and I can get better at it. And I have this group around me that can help me. And I think that can be a very powerful thing for weak students. Okay, so we've got this experimental section that appears to have done well. And for reasons that we sort of like. And so our next step is to put this thing into production. So we wanted to try it for a bigger class first. And we did that for Math 180. So since 2017, we've been running this in a single section course, 240 to 360 students. 2 hours of lecture. It's a 4-credit course. These are students who haven't seen calculus in high school. So it's 2 hours of lecture, 2 hours, a single 2-hour small class. And we've vastly expanded the size of the small classes because in the back of our mind, we had this idea that we're going to do this on a larger scale. And we just cannot do this on a larger scale unless the small classes have something like 60 students in them. And it's worth it. Okay, so starting next year, almost all of our calculus courses, so most formerly Math 100, 102, and 104, they're going to be taught using the small class model. Big 2-hour faculty-run lectures in the biggest rooms we can find on campus. And then 1-hour small classes with around 60 students. 60 students on average. It turns out classroom availability, as always, is the thing. And we're going to consolidate these things as well. So 100, 102, 104, we're just going to call them Math 100. They'll have different flavors. They're not, I mean, from the point of view of progression and credit, they are interchangeable. But we would recommend, right, that students who are interested in going to physics take flavor A. That students who are interested in going to commerce and social science take flavor C. And we're going to do this for integral calculus as well. 101, 103, and 105, we're going to call those all 101. As I said, the faculty members are going to teach the lectures. The instructors in charge are going to do a little bit of, so they'll set the assessments. They're going to run some professional development. They'll do less teaching. And most importantly, they're not going to do, it's not that they're not going to do any administration, but the consolidation allows us to have a central staff team that takes on as much of this administration as possible. So the idea here is that we want to kind of shove everybody into their correct starting position. We want faculty members doing what they're good at and what students expect them to be good at, which is kind of holding forth for large groups of students. Right? And we don't want them doing something that just profoundly frustrates them, which is just kind of maintaining spreadsheets and answering emails. We want novice instructors to have a better time. Highly supported, teaching the same thing multiple times every week with a run sheet where they know what they're going to teach. And they can focus on developing their teaching philosophy and learning what it is to learn without having to worry all the time about whether or not they're keeping up with the material. This is the goal, I think. Now, the next page is a little bit hyperbolic. I'm basically saying our hope is that this benefits everyone. I will say that the first year, there are probably going to be bits of it that are kind of a hot mess. And we're giving ourselves 3 years to get this right. And if we can't get it right, then we've always got a fallback position. Yes?
I think this is how many instructors are in these small class sections?
So the question is, how many instructors are in the small class sections? So it's 1 novice instructor and 1 undergraduate TA.
It's still 1 novice and instructor and 1 undergraduate TA.
Yeah.
As this has gone up from 20 to sort of 60.
Yes. Yeah, so at the moment, I'm running this in Math 180 right now. And it's, yeah, I mean, it's, at its least experience, it's like one master's student and one senior undergraduate student. Okay, who benefits? All right, so like I said, the hope is that everyone benefits. Students benefit, they get something that looks more like math. Novice instructors, this one is very big for us. They just get more support. They get more structure. Faculty instructors, in particular instructors in charge, get what will turn out to be a lighter load. And then, a few other people who we care a little bit less about, but I think they get some nice things. So the department gets its life simplified. I talked about flavors A, B, and C. The small class structure, it allows a little bit more granularity, right? So if a small boutique program wants a small class just for itself, there are some possibilities there. You can carve off 60 people who are really interested in, well, the Bachelor of International Economics is going to do this, right? You can carve off 60 students for them. We can carve off 60 students, a small class for 60 students in the Land 1 program, something like that. And those Land 1 students get to do some extra problems about land, I guess. And on the registration end, the consolidation anyway, will save us some headaches as well. At the moment, we have a fairly significant issue of students not always slyly, just often, I think, out of ignorance, signing up for Math 100 and Math 102 and Math 104. Right? We're just going to call it all Math 100. Okay. So a couple of closing thoughts. Thanks. As I said in the abstract, we in the math department, we are really operating at the end of our logistical supply line. My colleague Andrew Recknitzer, who used to do teaching assignments in the math department, would say, not without hyperbole, that if a faculty member got the flu, kind of unexpectedly, this is like 120 hours of scrambling. And at the end, the solution, it looks and feels like a Band-Aid. But we will have taken a section and cut it up and distributed it to grad students who are called in at the last minute to teach, even though we think they're not quite ready. So this, I think it helps us a little bit with it. It's mitigated, but I would say that it is a tactical project. It seeds that we have this logistics issue. And it asks, how can we operate under these conditions? Now in the math department, I think a bunch of other things that we're doing, I just came up with 3, but I have a few colleagues here, there are more, do fall into this umbrella of tactical-minded projects. So we've done quite a bit of work on our proofs course, Math 220, which used to be a small boutique course for math majors. And now is 10 sections in term 1, actually. So it's like 800 students in term 1 taking Math 220. And so transforming that course into something where it's not just an instructor who's in love with the course who teaches it once and then teaches it the following year, but a big team of postdocs and other instructors who have to be given materials and an online textbook, which we've written to teach this course. That's a tactical project. Finding engineers that can be kind of shoved into these large online courses, tactical project. Plum is our in-house grading tech that allows us to grade written stuff and assessments and exams at scale. Coming up with our own kind of battery of web work questions. These are all nice, crucial, tactical mitigation strategies. But before I get to the budget, in order to do this, I'm not going to go so far as to say something like Vantage College is necessary. But I will say something like Science 1 is necessary. So little protected spaces where instructors can try things out and be supported while they try things out. And maybe have a few extra resources thrown at them. not in perpetuity, but to iron out the wrinkles. I think these are really, really important things. But that notwithstanding, they are all tactical. So I want to end with this one. I mean, though it is beyond my pay grade, I think it's worth asking what the strategic goal is. Or can we do something about the root cause here? Can we do something about the logistical conditions that lead us to have to develop all of these tactics? Now, this seems to me to be the sort of thing that a very friendly associate dean could help with. Right? It seems to me the sort of thing that departmental leadership, particularly like departmental leadership in collaboration with other departments, could help with. I don't really know how strategy works. But I do know that we can only play the tactical game for so long. I'm excited about what we're calling the Math 100X project. But I'm also a little bit sad, right, that the project is necessary. And on that note of sadness, I'll conclude my remarks and open it to questions.